Today we're going to take a look at transforming functions. This is an Algebra 2 concept. So if you're in Algebra 1, this is a way to get a little enrichment. If you are in Algebra 2 or have taken Algebra 2, this is a great way to review. When we transform, there are three kinds of transformations we can be asked to do. We could be asked to do a translation. This is when you move a function up, down, left, or right. You could be asked to do a dilation. This is when you're asked to stretch or compress or shrink your function vertically or horizontally. And you could do a reflection, which means flipping the function over some kind of line, typically the x or y axis, but we really could do it over any line we wanted to. Now, the key to transformations is you have to think of this like an upgrade. So when you upgrade an app on your phone, you're installing something new into the existing software framework. That's what transforms the app into something better. It's not that you totally uninstall the app and then reinstall. Anytime you upgrade software, be it system software on a computer or an app on a phone, you are installing a chunk of something new into the existing software so that it can transform it. And that's exactly the same idea with function rules. When we go to transform them, we're going to install an upgrade. Now, the basic nature of upgrades, we got to look at this. Anytime we translate a function, we're creating a distance, a space, between the old function and the new function. Well, how do we calculate distance in mathematics? We do it by subtraction. If I want to know the distance between 10 and 4, I do 10 minus 4. If I want to know the distance between -1 and 6, I do -1 minus 6. So I can find distance by subtraction. When we dilate a function, so we stretch it or squish it, we're making a scaled version. Now, it's not a totally scaled, like a proportional situation, because we might just stretch it up. That's going to make the whole thing kind of stretch funny, not just get huge. So, still, it's a scale factor. How do we calculate a scale factor between two shapes? By division, of course. And when we reflect a function, what we're doing is changing a variable to its opposite form. So if I reflect over the x-axis, I'm taking a function and every y value on that function, I'm making it negative to flip it to the other side of the x-axis. Same thing with a horizontal reflection. If I'm reflecting over the y-axis, I'm taking every x that was once positive and making it negative. I'm taking every x that was negative and making it positive. So I'm just changing one variable to its complete opposite form. So then what's the deal for how we do transformations? Well, the first thing you got to do is determine what kind. Are you translating, dilating, or reflecting? Then you got to decide who's going to be affected. Will it be the x or the y? Then you have to decide, well, what's the upgrade you need to install for that variable that will pull off the requested transformation? Once you have that, you make that upgrade. You remove that variable and put in its place the upgraded form. Now, here's the thing with math. When we change the y variable, we always then simplify the rule to say y equals or f of x equals. When it comes to x, we simplify sometimes when we want to. Other times we don't because it might just be easier to leave it as it sits. And you just keep doing that. So every time you're asked to do a change, you take what you have, upgrade a variable, simplify if needed, then go back to the beginning. Get a new transformation, take what you have right now, transform it, and so on. So I think you'll find it easier to understand if we just jump in and do something. So let's say I start with y equals x squared. I want to do a translation. So let's say I want to move the graph 3 units to the left. Now, in math, we would associate -3 with left 3. That's just what our brain thinks. Left, oh, -3. How do we find distance again? We subtract. And moving left means changing x. So to find distance, I do x minus -3, the 3 left. And I get x plus 3. So my upgrade is x plus 3. So then I go over to y equals x squared. I upgrade my x by installing x plus 3 in x's spot. and I get y equals x plus 3 quantity squared. That's it. Now, if you are wondering if that really worked, feel free to pause right now, pull up Desmos, graph y equals x squared, and then graph y equals x plus 3 quantity squared. You should notice that the second parabola is shifted 3 units left from the original. Now let's do a dilation. Say I want to stretch this function vertically by a factor of 4. So in math, we would associate that with 4, like stretch by 4, that's 4. A vertical stretch affects the y variable. How do we find scale factors? Well, we do division. So I do division, y divided by 4. My upgrade is y divided by 4. So I go to y equals x squared. I upgrade y by installing y divided by 4. But now, because of the way math works, like especially if we're going to put it into Desmos, we like it to say y equals. So to undo that division of 4, I multiply by 4. So y equals 4x squared. Again, if you go back to Desmos, put in 4x squared, you should notice that it looks a lot like x squared, only every x value is going 4 times higher from the x-axis than it used to. So every y value associated with an x is now 4 times taller than it used to be. Now let's do a reflection. Say I want to reflect x squared over the x-axis. So think of the x-axis as the mirror. That means I'm going to flip the graph upside down. So if I'm flipping upside down, I'm changing my vertical orientation. So an x-axis reflection actually changes y. How do we do reflections? By opposites. So y has to become negative y. My upgrade is negative y. So I would go to y equals x squared. I would install negative y in the y spot. And now dividing by negative 1, I would solve for y. And there it is. So that's too easy, right? What becomes more complicated is if you want to do multiple transformations of the same function. And the order of those transformations really does matter. So you want to handle them one at a time. Upgrade something, see what you got. Upgrade the next thing, see what you got, and so on and so forth. So we're going to take y equals x squared, and we're going to run it through a series of a multiple transformation. So here it is. I want to move 2 to the right. Well, moving equals distance equals subtraction. So the upgrade would be x minus 2. 2 to the right is 2 positive. So I go to x squared, and I substituted the x minus 2 in its place. So I installed my upgrade. Now it says take that and now go 5 down. Well, moving, still a distance, still a subtraction, but down is to subtract negative 5 from y. So y minus negative 5, which is the same as y plus 5. So I go to where we are. I remove y and I put in its upgrade. Then because it was y, I'm going to solve by subtracting 5 to the other side. Now it says shrink horizontally by a half. Okay, shrinking means a scale. So that means division. Since it's horizontal, I'm shrinking my x variable. So I'm going to divide x by that 1/2. And I get 2x, because if I ask you how many halves fit into a whole, well, 2 halves fit into a whole. So that's 2x. So I go to my function, and I change out the x and put in 2x instead. Now I'm at 2x minus 2 quantity squared minus 5. And now let's say I want to cap the whole thing off by reflecting it over the x-axis. Remember that reflect means opposite, and x-axis is a up-down flip, so that changes y. So I change y to negative y, and then I divide through by negative 1 to get y alone. So that becomes negative parentheses, but then dividing minus 5 becomes plus 5. Now, you might be questioning me, saying this just doesn't seem right because it seems like everything you do is almost the opposite of what you think it should be. I move 2 to the right, but I say minus 2. I move 5 down, but I say plus 5. I shrink by a half, but it becomes 2x. So you might wonder, Is it really true? Well, let's prove it. To prove it, I'm going to go and use Desmos. I am going to show you the sequence of changes as they happen with the graph. So I start with y equals x squared. This is going to be the red graph, and it's going to remain for the entire picture. Let's look now at the first transformation, 2 to the right. I would expect this parabola should not change any of its shape, any of its appearance. It should just take every point and move it 2 to the right. Oh, look, it did. The vertex is 2 to the right. This point went over here. This point went over here. You can see that there is 2 squares of distance between the old red parabola and the new blue parabola. So it worked. Now, we're going to take this and move it 5 down. Remember, this is the second transformation. So now it's going to take the blue graph and move it 5 down. So think about what that should look like. Oh, there it is. You might say, yeah, but it got bigger, like wider. No, not really. Just remember, parabolas continue to get wider as they go up. So if you shift the whole parabola down, you're just going to see more of the wider section. But look right here. If I look at the bowl of the parabola, it went from here, down a square to the vertex, up a square to here, and those two are 2 squares apart. If I come look, you can see, there it is, down a square, up a square, 2 squares apart. But 1, 2, 3, 4, that vertex is now 5 lower than it used to be. So is this point, so is this point. So the transformation worked. Now, I'm going to shrink horizontally by 1/2. What that means is that every point on the green parabola is going to go halfway in towards the x-axis. So this point is going to come halfway in. This point is going to come halfway. So when you shrink horizontally, you're taking the distance that already exists and cutting that distance in half. So let's see if it works. That's the purple graph. And I know it's getting hard to see in this little spider web of graphs, but that purple graph, every point is now halfway back. Like this point on the green was 3 squares from the x-axis. Now it's 1.5 squares. So it has shrunk horizontally by 1/2. Now, if I'm going to reflect over the x-axis, it means I'm going to take this purple graph and I'm going to use the x-axis as a pivot point to flip the graph. So this point won't go anywhere. Every point above will flip to its exact location below. Every point below will flip to its exact location above. And there it is. That black graph is the final transformation. Take a look at that, and if it's bothering you, feel free to go back through the transformation sequence again. If you're feeling okay, why don't you try it? See if you can upgrade the absolute value of x. So complete the transformations and the table and the installation, and let's see if you can get it down to the final version. Go ahead and pause the video while you try completing this table. Welcome back. Let's see how you did. Here you go. Moving 1 to the left would be subtracting a -1, so I put in my installation of x plus 1. Stretching vertically by 6 means dividing by 6, so I divide by 6 and then solve for y. Reflect over the y-axis is a change to x. Changing x to -x, I get -x in x's spot. And moving 2 up means subtracting 2 to find distance, and so then I install for y and added 2. So the final transform function was y equals 6 times the absolute value of -x plus 1, all plus 2. Feel free to run the sequence of changes through Desmos just so you can see that it's doing what it's supposed to do each time. It's helpful. Okay, here's another one. You might notice if I flip back, I had a move 1 left, a stretch vertical 6, a reflect over y, and a move 2. I am giving you the same 4 transformations, but this time in a different order. Let's see just how much order makes a difference when you're transforming functions. See if you can complete the table. Feel free to use Desmos as a backup and come back when you're ready. Welcome back. Here's the sequence of transformations. You'll notice the upgrade column looks the exact same. Everything in the upgrade column is matching its transformation exactly the same. However, take a look at the final function. Because the vertical stretch happens after the move of 2, when you substitute the y with the y over 6 and multiply by 6 to clear it, that plus 2 upward shift gets magnified as well because everything gets stretched. A vertical stretch takes every point and makes it, in this case, 6 times farther away from the x-axis than it was. It's not that it just makes it 6 times taller. It's changing its distance to that y-axis 6 times as far as it used to be. So, kind of cool. It does make a difference which way you do it. Okay, here's a different function. Let's go to y equals x cubed, because that'll just give you something new to play with. Here are 5 transformations. Do all 5, use Desmos as your backup, and come back when you're ready. Welcome back. Let's see. First thing to check is your upgrade column. Make sure that you've got all the correct upgrades determined. Then take a look at the installation column. So I changed x to 3x, changed y to y plus 1 and solved. But now comes the fun part. Moving 4 to the left is an upgrade of x plus 4. But that means I take x and change it to x plus 4. Well, right now, x is being multiplied by 3. If I upgrade x, the entire upgrade will still be multiplied by 3. And I get 3x plus 12. Now you could leave it as 3 quantity x plus 4, but given that we already have parentheses, multiplying this out just feels better. Then I do my y reflection and my vertical stretch, and again, when I simplify that vertical stretch, I'm multiplying the whole thing by 5. That's the first term and the second term. So does it work for any function? Well, you betcha. Pick anything, and you can pick any transformations you want and you apply them the same way. The theory is the same. Determine the upgrade, make the substitution or the installation, and then simplify and see what happens. So feel free to try any of these just for fun. Here are some possible functions that you might not have thought to try because you haven't experienced them before. Try it, see what happens. So to close this out, why would this be valuable in any way? Well, computers all speak the language of math. Every app or software program you use has the hidden programming code that tells it what to do when given input. So mathematics is the underlying instructions for every app or software program. Well, think about any program or software that transforms or moves things. Given that I've watched a lot of movies during our shelter at home, I've been watching a lot of things that have computer graphics. The computer-generated images, CGI, animation. It's big and it has revolutionized special effects and what a movie can put into visuals. Now, to create a CG object and then have it move or flip or transform requires programming software by telling it with mathematics how to first create the image, and then once it has its formula for that image, how to move it, flip it, or transform it. Wait, that's just what we're doing. Get a formula that generates an image, then
tell it to move that image or stretch that image or flip that image. That is the basis of computer animated software. It's actually the basis of video games. Being able to determine mathematically if you aim a weapon at a target, does the game reward you with success or tell you you missed? There's mathematics behind that. Determining where your object will go, where on the screen layout it would land, and whether or not an object is there. This is all mathematics. So this transformations idea became the language that creates the softwares that you've probably used. Gaming, animating, it's really quite cool.